Hey everyone, it is Dr. C here with a special video podcast of all this science. We want to look at Lewis dot structures, in fact, Lewis do's and don'ts structures, right? So Lewis do's and not dots, but don'ts. Okay, Lewis do's and don'ts. Now, sometimes I rant about this as a university lecturer and high school chemistry teacher, and I hope some teachers are listening and some students as well, because there are some things that I've seen over the years that I think we can fix up right here and there. I don't want to sound like a grumpy cat at the beginning. You see here, I didn't have the copyright for the grumpy cat image, so I made one myself. This little drawing here. We don't want to be a grumpy cat, we want to be a happy cat, but we have to learn some things about it. So first of all, I'm going to tab to our friend the periodic table. I have removed the lanthanides and actinides. They're boring anyways. No, they're actually interesting, but they aren't going to be the focus of our topic today, which is on covalent bonded Lewis diagrams. We can talk about ionic Lewis diagrams as well, but the majority of issues arise when we're looking at covalent bonding. So we're going to be looking at group 8A, 7A, 6A, 5A, 4A, and a little bit of 3A. Aluminum can form some covalent systems. The usage of the A's is preferred. I know some of the young whippersnappers are now going 1 through 18 going across for the group numbers, but that method is the weaker method in my humble opinion when you're talking about Lewis diagrams. I like to use the older method because it makes more sense. I know I have 3 valence electrons in group 3, 4 in group 4, 5 in group 5, 6 in group 6, 7 in group 7, and 8 in group 8. Oh, except for helium, which only has 2. Hydrogen is special. Sometimes it's put in the beginning, in the middle of a periodic table. It has 1 valence electron. So I'm not going to look at the transmission metals. That's another story. The transition metals. I'm not going to look at the alkali or alkaline earth metals, or the metals way down here on the right hand side. Just the nonmetals and the metalloids. Okay, so some things that'll help you out is we know that hydrogens are terminal. They're at the ends of the bonds, and halogens are as well. And there's single bonds. Are there exceptions? Of course. Are we going to see many? No. So they form single bonds. And the central atom, and you need at least 3 atoms to have a central atom. Kids freak out about that too. I say, okay, what's the central atom and the oxygen molecule? They say, oh, I don't know. Well, there isn't one because there's only 2 atoms there. So there's the Lewis diagram for oxygen. Remember how to get the Lewis diagram? You just count up how many electrons are in oxygen. Total electrons? No, just the valence electrons, and there's 2 of them. So 6 plus 6 is 12, and then we can put 2 dots here, and then there's 10 left. So 2, 4, 6, 8, 10. We want to satisfy the octet rule, and we don't like that, do we? So we have to double buckle. When my kids were little, we used to double buckle. Don't tell anyone from soccer games and things like that, because you can't do that. Anyway, so we're going to take a pair of electrons and put them in the middle. And now we have 4 electrons, which is 2 dashes, right? 1 dash means 2 electrons. And now we have sigma bond to pi bond, fine. That's getting a bit advanced for what we're looking at right now, but we have the octet rule is satisfied for both of these. Okay? Now central atoms only happen with 3, and if I write OF2, I see some kids do this. They say, oh, there's an O, then there's an F, then there's an F. And I say, no, no, no. This is just known as the molecular formula, OF2. All it says is you have 1 oxygen and 2 fluorines. Some kids say, oh, well, the fluorine's a diatomic molecule because I learned when I was 7 years old, Hofbrinkel the clown, and fluorine always forms a diatomic molecule. added to an oxygen, and that is not true. It's just saying there's one oxygen atom and 2 fluorines. I could just as easily write it as F2O or FFO or anything like this. It just says that's how many fluorines there are, how many oxygens. The skeleton, I like to call it, or the bare bones, has the atom with the lower group number at the center. So oxygen is group number 6, fluorine is group number 7. So oxygen has to go in the center. Okay? And there are 6 valence electrons in the oxygen, 7 in a fluorine, 7 in the other fluorine. So I have to sprinkle 20 valence electrons. And I don't care where these electrons come from anymore. They're all indistinguishable 20 electrons. I like to think of them like as dumplings in soup or something like that. So you spoon in to a big pot 20 dumplings, and now you spoon out with a ladle the 20 so that everyone's satisfied. They aren't hungry anymore. There's 8 valence electrons around them. Sometimes they're lone pairs, sometimes they're shared pairs. So fluorine's going to have 3 lone pairs of electrons and 1 shared pair to the oxygen. The other fluorine the same because of symmetry, you can see that. So I got 6, 12, 14, 16. There's 20 altogether. I got 4 electrons left. Well, the fluorines are both happy. Oxygen's hungry, so it wants 2 more electrons. And there you have it. That is the Lewis diagram, or Lewis dot diagram, or Lewis structure, or electron dot diagram. All those words. Lewis structure is the easiest to say for oxygen difluoride. I'm not saying this is a linear molecule. It ain't a linear molecule. This is a angular molecule, bent, V-shaped. Those are all synonyms, bent off of 109 degrees. And that's getting all into the VSEPR molecular geometry stuff. But we can't get there yet. We have to make sure that our Lewis diagrams are correct. Now, if some teacher marks this wrong, you give me an email, okay? If some teacher says, oh, this is wrong, this is not the Lewis diagram for oxygen difluoride, you tell that teacher that Dr. C said, sure it is. All the Lewis diagram does is tell you which atoms are bonded to which other atoms, whether it's single, double, or triple bond, and where the lone pairs are. Okay? It doesn't directly tell you the geometry. So each of these is equivalent. Now sometimes you'll get a teacher who will tell you that the, let me just zoom down here. Okay, zooming down to the next page. And you can go back and forth in the movie to look at other pages. They'll tell you that the more electropositive atom is in the center. Guess what? That isn't always true. So let's not say that anymore. Teachers, let's not say that anymore to our students. Let's tell them that it is the more, let's start again. The central atom is the atom which has the lower group number. Because if I go to oxygen diiodide, OI2, oxygen has a higher electronegativity than iodine, so you would think that iodine, if you're talking about this electropositive, electronegative stuff, iodine would be in the center, but it's not in the center. Halogens like to be at the end. Oxygen is in group number 6, iodine is in group number 7. So it's a more consistent rule if I use the rule of the lower group number is the central atom. Now if there's 2 central atoms or 2 interior atoms, well, we can get to that in a few minutes. But here's one fallacy that I hope we don't tell our students anymore. Okay? What are some other good things here? When you're making oxygen diiodide, I mean, you can do the dots first. After a while, you'll quickly put in dashes instead. But let's always use dots. Okay? I see some people use open circles. Some people use X's. Some people use different colors or different symbols for each atom which is contributing to the bonding in the covalent system. That is bad and that is dangerous because what happens, and I always give this on a test, carbon monoxide, CO, right? So I see people do this. They have carbon, it's got 4 valence electrons, so they put a 4 and they have oxygen with 6 and they make them different colors. It looks like some football thing going on here, and then they cross them over like this, or pair them up and you got O2 left on the oxygen. They write weird things like this, okay? There's no quadruple bonds. that doesn't happen. Some people can argue in transition metals, have some stories about that, and delta bonds and all this. But in everyday cases that we look at, covalent bond, main group representative elements, you don't get quadruple bonds. So don't tell anyone there's such a thing, and stop doing this kind of stuff, okay? Because it is wrong. And it's coming from the fact that you're trying to maintain the identity of the electrons with the atoms from which they came. Don't do that. You just have 10 electrons buzzing around, 6 protons and 8 protons. How can we satisfy the octet rule? That's all you have to do. Don't overthink it. So I got a carbon and oxygen. So I got 2, 4, 6, 8, 10. That's the only way that we can get the Lewis diagram to satisfy the octet rule. And yeah, there's a lone pair on carbon. Okay, so be it. That's what it is. Okay, so carbon dioxide. Carbon is in group 4, oxygen is group 6. Carbon is in the center. Carbon gives you 4 valence, each oxygen gives you 6. So you have 16. 2, 4, 6, 8, 10, 12, 14, 16. Oxygen is happy on either side. Carbon is happy. And just go with it. Just try it. You know, if you have a whiteboard at home, try it on the whiteboard and erase it, or use old calendar paper and keep erasing and keep trying, and you'll start to find similarities. If I go to carbon disulphide, well, I'm using the periodic table to my advantage because sulfur is in the same group as oxygen. So I don't have to reinvent the wheel if I use the periodic table. Now, one hotshot kid is going to say this: oh, well, I can get 16 if I, and the octet rule is satisfied if I make one carbon oxygen a single bond and the other one a triple bond. 2, 4, 6, 8, 10, 12, 14, 16. Yeah, you can. Or you could make the other one a single bond and that a triple bond. But where's the symmetry? You don't have the symmetry anymore. There's no reason on Earth that one carbon oxygen bond should be more like a single bond and the other carbon oxygen bond be more like a triple bond in carbon dioxide. Like, what would be the reason for that? Does the Lewis rules work? Yeah, up to a point. If I now would go into the world of formal charges, this oxygen would be a -1 formal charge, this will be a +1, and you want to minimize formal charges, get as many 0 formal charges as possible. So this will be ruled out. But even before the world of formal charges, just because you can satisfy the octet rule doesn't mean it's the best representation. Symmetry can be very helpful in the business that we're looking at. Okay, so let's see what else I have here. Oh yeah, here's one that I see all the time. I'm going to scroll down a bit. Okay, here we go. There's, okay. I see this all the time. Kids see something like CH2F2, and they aren't sure what the central atom is. Well, hydrogen's always terminal, fluorines are always terminal. It's not the difluorine molecule, so carbon's in the center, and molecules like to be compact, okay? If there's just a few atoms. They don't like to be chains. I know we can get to polymers and talk about all long chain molecules and things like that, but small molecules, nice compact, so hydrogen's around the carbon, fluorine's around the carbon, and I can now finish it off. So carbon has 4 valence, each hydrogen has 1, and each fluorine has 7. So I get 4 plus 2 is 6, plus 14 is 20. I see kids sometimes use calculators to add that. Really? Go ahead. You want to use calculators? Go ahead. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, I would use a slide rule or an abacus to do that, to tell you the truth. Okay, I won't make my joke about the Swedish rock band on Valentine's Day would be an abacus. I won't do that. Okay, so there you have it. And some kids say, oh, well, is that the same? What if I do this? FH, FH. Yeah, it's the same. Okay, it's telling me that there's 2 fluorines, they're bonded to the carbon, and 2 hydrogens are bonded to the carbon. They're all single bonds, and I have 3 lone pairs and 1 bond pair associated with this fluorine and the other fluorine. It's not telling me the geometry. The geometry would be tetrahedral, and that would be me doing a grumpy cat, happy cat on Vesper. Boy, maybe one day I'll do that. That would be fun. Okay. So what were some other ones that tick me off and that I see? This one here, I see odd things sometimes with this. NO3 minus. Kids freak out about this. Okay, this is a molecular ion, or we could call it a polyatomic anion. Poly just means two or more, so we have a polyatomic grouping here. We have 4 atoms all together. Nitrogen likes to be in the center because it is in group 5, and oxygen is in group 6. So I got 3 here. The oxygens try to surround the nitrogen as much as they can. Really, this is the technically conjugate base of the strong acid nitric acid. So NO3 minus. So nitrogen gives me 5, each oxygen gives me 6, and I have 1 more, so I have a total of 24 valence electrons. The kids freak out about that negative sign. What does that mean? It just means there's 1 more electron hanging around in the system, so it's 24. I'm always going to use even numbers of electron. There are some oddball cases like nitrogen monoxide where you have an odd number of electrons and you put the extra electron in nitrogen, and you could fight about that. But here we got NO3 minus. So I have 24 electrons. So I have 2, 4. I can have a double bond here, and then I can keep going to make the octet rule satisfied. And I like to put square brackets and then the minus sign. So does that work? 6, 12, 18, 20, 22, 24, 26, 28. Way too many. Way too many. Let's count again. 6, 12, 14, 16, 18, 20, 22, 24. Okay, if I counted right, that's good. And of course, you could put the double bond over here or here. In fact, as you'll learn, there are 3 resonance structures associated with the nitrate. And the mix of them will give you what's called a resonance hybrid. And each NO bond will be between a single and a double bond. So these are just some of the things that I've seen over the years. Chemistry teachers, if you've seen some other ones with Lewis structures that annoy you and you have an idea for making it clear for the students, let me know. Send me a email to allthisscience@gmail.com. All this science, better spell science right, @gmail.com. And students, if you're stuck on any Lewis diagram stories, send me an email too, and I'll help you out, or I'll try anyways. Because we don't want grumpy cats, we want happy cats. All right, that's a good happy cat. Let's count the eyes. We got 2 eyes. We got some teeth in there, and everything's satisfied. Octet rule satisfied. Octet rule satisfied. No, that didn't work, did it? Okay, until next time. This is Dr. C, All This Science.